Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to be talking about section 9.2 in Calc 2, but also we'll be doing a little bit of 9.1. And that's because in this chapter, we're going to be addressing the concepts of differential equations. And instead of making a separate video for 9.1, because 9.1 is relatively short, I'm just going to mesh it into here. So before we go into 9.2, which has to deal with direction fields and Euler's method, we have a little bit to talk about from 9.1, which introduces what a differential equation is. Now, a differential equation, or what you'll commonly hear me say, a diffie-q, just taking diffie and EQ. A differential equation is an equation that contains some function and at least one of its derivatives. Note that we say at least one of its derivatives. So it could have just one derivative of it, or another derivative of it, maybe a different degree of the derivative, so like a second or third of it. And those derivatives typically stand for a rate, like distance in respect to time, like velocity. We will say that the differential equation has an order that's equal to the highest derivative that you see present in the equation. And what I have here are a couple examples of differential equations. First, in differential notation, which is like dx over dy, so differential of x with respect to y, and then the second derivative of x with respect to y. You can also represent that with prime notation. A lot of people like this because it's cleaner. The downside of prime notation over differential notation is that differential notation tells you to what variable you're taking it in respect to. For example, when I see this second equation, which has y with respect to t, I don't know that I'm with respect to t in the second version of the equation with prime notation. However, when we're actually computing, prime notation is fine because we know what the equation of y is, or one of the derivatives or something, so we know what variable we're working with anyway, so it's not the biggest deal. But if you're giving somebody the general form of something, sometimes differential notation is easier. I recommend being familiar with both notations, though, and knowing what they both mean. Okay. Now, when we solve these, we're not necessarily going to get numbers like we would for solving volume or area or integrals before. We're going to get solutions that are families of equations, and not just equations that have a plus c necessarily at the end of that, which means plus or minus some constant at the end. We are going to have some variable constant, but that might be within the function itself. And those are going to be the solution sets that we create. If we are given an initial condition, we can then take that solution set and narrow it down to a very specific equation that solves for that initial condition. The initial condition just being a coordinate pair. And all it takes is plugging that coordinate pair in to find what that solution set is. So, as a quick example of this, again, before we dive into 9.2, we have that we're going to show all members of y equals parentheses c minus x squared to the negative 1/2 are solutions of y prime equals xy cubed. And then we're going to find the solution for the initial condition of y of 2 equals 2. Okay, so we already have the solution given to us. This is the equation of y. And what we're going to show is that this is true, that these are solutions for y prime equals xy cubed. Now, there could be other solutions to this, but these are a family of solutions that we found. In order to prove this, we simply have a left-hand side and a right-hand side, and all we need to do is find what both of those are. Well, the left-hand side, I'm just going to take the derivative of y, which in this case, I'm taking c minus x squared to the negative 1/2, and I'm taking the derivative of that with respect to x. So that's going to pull the negative 1/2 down by the chain rule. This will become negative 3/2 now, and then I also multiply by the derivative of the inside, which is negative 2x. The negative 2 and that negative 1/2 will cancel, so we just have x times c minus x squared to the negative 3/2. Then if we can confirm what the right-hand side is, which is xy cubed, and if we show that's the same thing, then we're good. So xy cubed says take x and then take y, which is c minus x squared to the negative 1/2, and then cube that. All that's going to do is take that exponent of negative 1/2 and multiply that by 3, and we get negative 3/2. And therefore, since we have this is equal to this, then we say that therefore y prime equals xy cubed for the solution set. So this family of equations where I could plug in really anything in for c and we get a different equation would all be solutions for this. Let's find what specific solution helps us have y of 2 equals 2. So if we plug in 2, we get a response of 2 as well. That's relatively simple. We just take our original equation and we plug in. We just solve for c like we would normally. So y is 2, x is 2, so that's going to be 4 to the negative 1/2. Square both sides and then take the reciprocal. We get 1/4 equals c minus 4. Add 4, which is 16 over 4, and we get 17/4 equals c. So we have y equals 17/4 minus x squared to the negative 1/2 as our solution. Nice and easy. All right, so that's in general what differential equations are and how you can solve for what we call an initial value problem or initial condition problem. Now, I talk about those because we are going to be doing a lot with differential equations, but we're going to dive more into those as we go. However, if you notice in that problem, we had the solution given to us. We had the solution of the formula that works for this differential equation given to us. However, that's very often not going to be the case, particularly in real life cases. And there's also a lot of differential equations that are just not possible to solve, or at least definitely not right now. And so what we're going to talk about here in section 9.2 is how we deal with these quote-unquote unsolvable differential equations, or how we can view what they would look like without knowing too much else about differential equations. And we have a couple different methods for that. We have both direction fields, which are sometimes also known as slope fields. And we also have Euler's method, which we'll get to later on. More or less, a direction field is basically a magnetic field. What we're going to do, and the reason why it's also called a slope field, what we're going to do is plug in various coordinates and find what the slope would be at those points. So for example, I take the coordinate 1, 1, I think about what the slope is, and then I'm going to draw a little line that represents the tangent line with that slope. That's what a direction field is going to look like. Okay. Now, these are going to be for what we call first order differential equations, where we have the first derivative given to us, and that's really the highest one that we have. So what we're going to do here is show what happens when we sketch the direction field for the differential equation y prime equals x minus y. And then we're going to use the field to sketch the solution for the initial condition of 0, 1. Okay, so we'll get to that second part in a moment. But let's start to sketch this. And again, all we're going to do is plug in some points. So let's say x and y. We can start plugging in some points. And then we'll get our resulting y prime. Okay, so say x is 0, y is 0. 0 minus 0 is 0. Nice. How about x is 1, y is 0? So just another coordinate pair. That's going to be 1 minus 0 is 1. 2 and 0 is going to give me 2. If I do maybe 0 and 1, I get 0 minus 1 is negative 1. 0 and 2 will give me negative 2. So I'm starting to get some points here. Maybe if I do 1 and 1, which I didn't do, 1 minus 1 will give me 0. 2 minus 2 will give me 0. Again, I'm getting these y primes because the equation that was given to us is simply x minus y. So I'm just taking my x value, subtracting my y value to get y prime. Now, all these points represent, again, the slope of the line. And so how we're going to represent that is a small tangent line that we draw that represents that slope. All right, so let's do that in blue. So at 0, 0, so at coordinate point 0, 0, I have a slope of 0. A slope of 0 is a horizontal line like this. So that's what I'm going to put. Note that I'm not going to continue it too far. I'm just putting it centered at 0, and I just have that line. At 1, 0, which is right here, I have a slope of 1. A slope of 1 looks like this. If I just think about an xy curve that has a slope of 1, that means it would be a curve that would continue like this. That would be a slope of 1. At 2, 0, I have a steeper slope of 2. So I get something steeper like so. And you can extrapolate from that. We can see a pattern already that as I go further in this direction, this is getting steeper and steeper and steeper. Now if I do 0, 1, I got negative 1. So at x is 0, y is 1, I got a negative slope, so I get this instead. And then at 2, I get negative 2, 3, 4. It keeps getting steeper and steeper. And then at 1, 1, we saw again a slope of 0, which is going to be horizontal line. Same thing at 2, 2. Now we should be able to continue this just kind of looking at the graph really. So say x is 2, y is 1, so that's 2 minus 1, that's 1. So I get a slope of 1. 3, 1 is 2. Let's make that a little bit better. But notice where I'm getting some of these common values. At 0, 1, I got a slope of 1. At 2, 1, I got a slope of 1. I'm also going to get that at 3, 2. Going to get a slope of 1. And also here and here. And it's going to continue on. So I'm seeing this pattern. If I ever take these values and subtract them, I'm going to get a slope of 1. Likewise, the pattern I saw for the horizontal lines, the slope of 0, happen there, at 5, 5, 4, 4, negative 1, negative 1, negative 2, etc., etc. All these, I'm seeing these patterns. And so I'm seeing all these patterns that continue diagonally, so I'm going to just continue that. So here is the slope of negative 1, so negative 1 will also be here, and here, and here, and here, and I'll keep going. And basically, this is what I'm going to build. This is the direction field, more or less. Steeper slope. Now, you don't need to do all the coordinate points, but you should be able to do enough to get an idea of what the magnetic field looks like, or what the direction field looks like. Again, this is why it's also called a slope field, because all you're building are these really steep slopes. Now, I just am starting to fill these in a little bit more haphazardly now. But you see the way I'm doing it, I'm starting to get this picture where I get this this diagonal line here, and then as I move over to the left and up, it's getting steeper and steeper and steeper. I'm seeing that general trend. Whereas this direction, slope of 2, slope of 2, slope of 2, 2, 2, 2, 2, then 3 and 3 and 3. So these are also getting steeper and steeper and steeper as I go. So the further and further I should go, for example, if I had this point of x is 5, y is negative 5, that'd be 5 plus 5 is 10. So that's a very, very steep slope. So a little bit more haphazardly, you don't need to technically be too careful as long as you got the general pattern. And that's more or less what the direction field will look like. Really, start to see the ones that have pretty low slopes, so between like negative 3 and 3. Then after that, they should just get steeper and steeper, and you should be able to see a trend. All right. So that would be our direction field. It takes a little bit of time, but not too bad. It also asks us to take the initial condition of 0, 1 and graph the line for that. Well, in order to do that, I want to find where x of 0, y of 1 is. So x of 0, y of 1 is right here. And what I'm going to do is graph the curve that passes through that. So I'm going to I'm going to consider this slope here, which we considered was -1. So maybe not as steep as that. -1 should look more like that. And then what I'm going to do is, after I continue that, I'm going to follow the direction field. Again, consider the magnetic field. So I'm going to continue in that pattern. As I continue up in the y direction, it gets steeper and steeper, so this should look something like this. Whereas as I go higher and higher in the x direction, this is starting to approach this line. So I should probably get something like this. So that would be the curve here. We're just following the general trend of this magnetic field. Okay. I do recommend when you do these, color really helps. So if you do happen to have another colored pencil or something else to designate direction fields, it can be a lot easier to do that. Okay, let's do a couple more examples. All right. Oh, yeah. Sometimes you'll also be asked for what is sometimes known as equilibrium solution. The equilibrium solution is a solution that results in a derivative of 0 everywhere. And you notice we got derivative of 0 at some places, at 0, 1, 1, 2, 2. Our equilibrium solution would be right here, going across this. And that line is defined by y equals x, and then the y-intercept is -1. So this is the equation of y equals x minus 1. Oh, sorry, not y equals x minus 1, not that line. Where slope is 0, which is here. So you the horizontal lines. So that's just at y equals x. Yeah. So that would be our equilibrium solution. All right, sometimes it'll be a horizontal line, sometimes it'll be a diagonal line, and you can usually graph them. Again, these are going to be pretty simple first order, so they shouldn't be too complex. All right, so we're going to do a couple examples here, and then in both of them, we're also going to define what the equilibrium solution would look like. So we have here, sketch the direction field for the differential equation 2 minus x, and then we'll find all equilibrium solutions. Okay, so we have y prime equals 2 minus x. Well, that's kind of interesting, because if you notice, unlike before, we don't actually have any value for y on this side. So when I plug in coordinates for x and y is going to be completely irrelevant. Really, I'm going to take any x coordinate I have and take that away from 2. So 0, 1, 2, 3, 4, 5, 6, or anything like that. 0, 1, 2, 3, 4, and 5. Well, 0 and whatever y is, so I'll just say whatever number this is for y, it's not even going to matter. If I plug in 0, I get 2 minus 0 is 2. 2 minus 1 is 1. 2 minus 2 is 0. 2 minus 3 is -1. 2 minus 4 is -2 and -3. And I can also do the same thing for x's -1 and -2. 2 minus -1 is 3. 2 minus -2 is 4. And it doesn't actually matter at all what y is, because y is not part of that equation at all. So then creating this direction field is going to be even easier. I see at x of 2, I have a slope of 0. So at x of 2, I have a slope of 0. And that's going to be true at all instances for y. And then aside from that, at x of 1, I have a slope of 1. And that's true for all instances of y. And then at x of 3, I have -1. Notice that I'm focusing just on the simpler slopes first, the ones that are easier to write, 1, 1, maybe 2 and 2. So 2 would be here, getting steeper and steeper and steeper. It's a lot harder to represent 2 very accurately. Then -2, likewise, a lot harder to do. After that, though, we see the general trend that it's just going to get steeper and steeper and steeper, so I don't need to be too careful after that point. These are also very nice to build in calculative functions. So if you have a calculator or a something that can build this. Maybe if you're familiar with Python, then you could do that. Okay. Now I wasn't too careful, but I do see that overall trend looks relatively nice. Maybe this curve down here looks a little bit too shallow, something like that. All right, so that would be my direction field. Then my equilibrium solution, again, that's where the slope is 0, which is right here. That equilibrium solution happens at x equals 2. That's my equilibrium solution. Okay. Not too bad. Let's do another one. Again, this one, pretty easy because here we have another equation where we don't have anything for one of the variables. So one of these variables is not going to be relevant. In this case, we have tangent of 1/2 pi y, which means there's no x's. So I don't care what x is going to be. It can be completely irrelevant. However, y is going to be an interesting question. If I plug in y of 0, maybe if I do 1/2 would be a good one, and you'll see why in a second. 1, 3/2, 2, 5/2, something like that. So if I plug in 0, I get tangent of 1/2 pi 0, so tangent of 0, and tangent of 0 is 0. Tangent of 1/2, so that's tangent of pi over 4 actually, which has a slope of 1. And then tangent of 1/2 pi times 1, so tangent of pi over 2 is undefined, which means that it's a vertical slope. And then I keep going from that. 3/2, if I plug in 3/2, I get 3 pi fourths. That's going to put us in quadrant 2, and over there tangent is negative, so that's -1. If I plug in 2, I get tangent of pi, which is 0. 5/2 will give us 5 pi over 4, which is in quadrant 3. Tangent is positive over there, so that's a +1. And I keep going like that. You see this pattern here, which this pattern should look very familiar from tangent itself. If I plug in the next number 3, I'm going to get another undefined. So let's start graphing this. We probably should be able to see the pattern after that. So at y is 0, I get a slope of 0. At y of 1/2, I get a slope of 1. So I'm going to be a little more intricate here. And then at 1, I get an undefined slope, which is a vertical slope. Directly vertical. And then 3/2, I get -1. Starting to see how this looks. They should make more or less natural curves as you see them. So like if I start at the x-axis and I start going up, I see this going this way, so curving back. And then at 2, we had another slope of 0. Five halves, we have a slope of 1. And now we see this pattern repeat itself. So this pattern is going to repeat here, it's going to repeat here, and here, and here, every 2 that we see. So I should be able to start to fill that out pretty quickly. So slope of 0 should show up at every even amount. So if at 0, 2, 4, -2, -4. I have vertical lines at every odd amount. Then I have either 1 or -1 at the halves. And again, I should see that pattern keep repeating itself. So they're kind of like asymptotes. All right. You'll also notice as I'm completing this, you'll notice that there are actually multiple solutions in this case for the equilibrium solutions. instead of listing them all out, which is impossible, as you were to continue this, you would have infinite amounts of solutions. We should be able to list those out in a more intelligent manner. Should be something kind of similar to what you did in trig. Let's start finishing that off pretty quick. Okay, so we have that general pattern. We see the equilibrium solutions at 4, at 2, at 0, 2, -4. And we notice that that's y equals all of those. So we have the equilibrium solution at y equals, in this case, 2k, where k is an integer. An integer is represented by that z. So that would be my equilibrium solution. If you haven't seen this notation, this is k is an element of the set of integers. So that's k element of integers. So that's what I'm saying right there. Okay. So overall, those are direction fields. Sometimes they can be pretty simple, particularly if one variable is not present. If they are both present, then you have a little bit more complicated like we did in the first example. But overall, not too bad once you start to see a pattern. Now that's the graphical way to do that. And notice in all those, we didn't need to find what the actual solution was. We just found what the slopes looked like and graphed those. There's a way of numerically finding it, though, and I'm not algebraic yet. We'll deal with that in a moment in the rest of chapter 9. But if I just want to numerically represent the differential equation, we can do what is called Euler's Method. And the Euler's Method is basically finding what we just did in the direction fields and finding what a graph would look like given some initial condition. So if I have some initial condition, what the solution would look like graphically, what the points would be. And the way that this works is more or less we start with the initial value. So right here, we start with the initial value, we calculate the slope of it, and then if we have a value and a slope, so a point and a slope, we can use point-slope form and calculate the next value in the sequence. The next value in the sequence, though, will depend on the step, which we represent with an h. The step is how far do we go until we recalculate. So whatever my initial point is, how far along the x-axis do I go until I recalculate and find my next point. The lower the step is, the more accurate your graph will be. The longer the step is, the more the graph becomes incorrect to what the actual solution should be. You can think about this like if my curve looked like this, so like e to the x, and I started here, well then I draw a tangent line there because I'd find that slope. And maybe I recalculate after I go a distance of h. Then I find a new slope, and I start continuing along that manner. Then after another h, I recalculate. Then I find a new slope, and I recalculate along that manner. Then a new slope, and a new slope. If you notice, as I'm going farther and farther out, I'm getting less and less accurate to what the graph is. And that's going to continue to happen, particularly with this graph where y starts overtaking x quite significantly. So that's more or less what we're doing. And so we're going to have a list of points that designate my approximate solution. Now overall, this is taking in the point slope form. So y1 minus y0 equals m times x1 minus x0, stuff like that. However, usually y and x, but what we're going to do is try to solve for the next value y. Using y0 and x0, my initial point, and the distance from x1, x0 is actually just h. That's going to be your step distance. The slope is what we calculate using the function, so overall we get the formula y0 plus the step times the slope. Or in general, we have this equation here to find any point at any given point. So if you start at the first point, you can find the second one. If you start with the second point, you can find the third one, and on and on and on. So that's what we're going to be doing here, and we're going to show an example of that down here. So we're going to use Euler's method with step size of 0.5, so we have h is 0.5, to construct a table of approximate values for the solution of the following initial value problem. We have y prime equals x minus y. We have y0 equals 1. And notice that this is the exact same formula we did in example 2, the first direction field we did. Now we're actually going to calculate the formula for this. Okay, in order to do that, what we're essentially going to be finding is again a list of points. So the first point that we have is the points that are given, 0 and 1. After that, what we're going to do is we're going to start to plug those in to find the slope. So we have for point 2, we have y prime is 0 minus 1, so negative 1. And therefore, to find y2, using the formula above, not y squared, y2, if n is 2, that means we're going to take the previous point, n minus 1 is 1. So the first y point was 0, 1, so that's 1, plus the slope, which we found to be negative 1, or plus h, which is the step, which is given to be 0.5, times the slope of negative 1. So it's 1 minus 0.5 is 0.5, and that's going to be our next point. It's going to be our next y point. Now what about our x points? Well, our x points are all defined by the step. So 0 plus h, which h was 0.5, gives us 0.5, plus another h gives us 1, plus another h gives us 1.5, plus another h gives us 2. So the x value should be easy. The y values are the ones that take a little bit. The third point, y3, is going to be the previous y coordinate, which is 0.5, plus the step, times the slope, which is defined by x minus y. In this case, x minus y is 0.5 minus 0.5. So that's 0 times 0.5 is 0, plus 0.5 is again 0.5. The fourth point, okay, take our previous coordinates, so y is 0.5 yet again, plus our step, times x minus y, where x and y are our previous coordinates, so 1 minus 0.5. So we get 0.5 times 0.5 is 0.25, plus the original 0.5 is 0.75. Okay, so we've changed. And then we can find our fifth point using this method as well. So our previous coordinate is 0.75 plus our step times our previous coordinates subtracted, so 1.5 minus 0.75. That'll give us another 0.75 times 0.5, gives us 0.375 plus 0.75 will overall give us 1.125. So that's how we find all of our points. Notice that in all these, the thing that never changed was our step. Our step is always consistent through. Every other time, what I would then take are the coordinate pairs, again defined by our previous solution. Now if I graph this, all I need to do is plot these points. So x is 0, y is 1 is right here, 0.5 and 0.5 is right here, 1 and 0.5 is right here, 1.5 and 0.75 rises up a bit, and 2 and 1.125 is up here. So we start to see this curve. And if we compare that to the direction field we made back in example 2, I'm going to scroll up here. So back in example 2, we get a curve that does look pretty familiar. So that is also right there, just zoomed in. Again, this becomes more accurate the further out you go from your initial point. So my initial point was right here. The further out I go from that, the more inaccurate it becomes. All right, let's do one more example of this. Now for these, you typically won't have the table and the graph set up, so you're going to have to do this yourself, but the tables aren't too bad to set up. And I just have listing like what coordinate pair I'm finding. Okay, we're going to use Euler's method again with step size of 0.5. That's going to be a very common step size to construct a table of approximate values for the solution of the following initial value problem. So we have dy dt equals cosine of y. That means we don't have x's this time. So in this case, our x variable is actually t. So this is going to be t, and this is going to be y. But with all of our points, we have our step of 0.5. We have our equation, which is essentially y prime equals cosine of y. And we have y0 equals 1. And it also gives us 0 to 2. So we actually have bounds this time in terms of how far we're graphing. Sometimes you'll be given bounds, sometimes it just says find 5 closely connected points. So 0 to 2 makes it very easy. I start at 0, go up by my step, up until I get to 2, which is why I only put 5 rows here. My initial point was 0, 1, so I put that point in here, and then I can start to find what the next few are. The second point is going to be the previous coordinate, so 1, plus the step of 0.5 times the slope, which is going to be defined by cosine of just y. In this case, I actually don't care what t is at any point. So this is just cosine of 1. Now because it says 1 and not 1 degree, we assume that this is in radians. So if we assume this is in radians, we can calculate this appropriately. 1 plus 0.5 times cosine of 1. If you do that in your calculator in radians, you'll get 1.2702 approximately. I'm going to round all these to 4 decimal places. Why not? Try to keep as much accuracy as you can, I guess. And then for the third point, we continue along this fashion. Now my y-coordinate is 1.2702 plus 0.5, the step, times the slope, which is defined by cosine of my y-coordinate, 1.2702. So I'm actually never even going to use t in this equation. If we do that, you get 1.4182. So that's my second point. The next two are going to continue along in this fashion. 1.4182 plus 0.5 times cosine of 1.4182. And if you approximate that, you get 1.4942. You can see why I'm starting to round pretty closely, because these answers are getting really close to each other now. And if I do that one more time, you get 1.5325. And then if we graph these points, 0 and 1 are right there. 0.5 and 1.27 is maybe there-ish. 1 and 1.4 is maybe there. 1.5 and 1.49. Around the same place. Maybe I went a little too high there. Such small incremental changes is hard to represent. We get a graph that looks kind of like this. Note that in this case, I'm not going to continue the line. I'm not going to say like, oh, it goes this way and then this way, because I just wanted from 0 to 2. So I'm only going to graph the one section that I wanted. It just said to graph the time from 0 to 2 and stop there. However, if we do try to consider this, this kind of looks something similar to like square root of x plus 1. It almost, or square root of t, I guess, plus 1. It almost looks like this. I'm not saying that it is, but it kind of looks like that formula, because the square root of function looks like this. So kind of similar to that. All right. With that said, that's everything that you need to know in terms of direction fields and Euler's method. If you have any questions, feel free to put those in the comments below or ask your instructor directly. I hope you have a nice day.